بسم الله الرحمن الرحيم. محاضرتنا اليوم راح تكون continuation للمحاضرة السابقة. احنا في المحاضرة السابقة غطينا موضوع الستيت controllability. اليوم راح يكون عن موضوع related للcontrollability بس بتعلق في الاوتبوت controllability. بالتالي فيما يتعلق في الاوتبوت controllability احنا بنحكي عن في الاوتبوت controllability بنحكي عن اللي هي how to control the output variables instead of the state variables. وبالتالي شو المفهوم ما يعادل مفهوم الستيت controllability. اوكي، اذا افترضنا في عندنا state space model ABCD فالشرط حتى تكون completely output controllable if it is possible to generate or to construct an input unconstrained input vector اللي هو اليو that will transfer any given initial value of the output to any desired or any final value over a finite interval of time t which is between t naught and t final. So the concept of output controllability is very close to the state controllability, with a minor change that we are speaking about the output vector, not the state variables. So in the state controllability it was very similar. So the system was, if you remember, the system we say that the states are completely state controllable if it is possible to construct in the same manner an unconstrained input vector u that will transfer for the state controllability any given initial state from x of t naught to any final value or desired value of the states x of tf in over a finite interval of time t between t naught and tf. So the concept is similar. And for output we are changing, for output controllability we are changing the thing to be controlled, okay, from the states to the output vector. So instead of controlling the states in state controllability, in output controllability we are controlling the output vector, which is y. Okay, so this is the main concept of output controllability. And here we will generate a new matrix. It's called output controllability matrix, QCO. So we have given it the symbol QCO, okay, which is output controllability Q matrix, and it will be of this order: P multiplied by n multiplied by n plus 1 if we have m inputs and p outputs. And this matrix is generating using equation 6.4, which is close and similar to the controllability matrix. If you remember the controllability matrix, it was b ab a squared b till an a to the power n minus 1 multiplied by b. So if we compare QCO with the QC that we have previously covered, then we will notice that C is multiplied by all of these terms. C is multiplied by all of these terms, a pre-multiplication. And the second difference is that we are adding the D vector at the end of this QCO. So what is the necessary and sufficient condition for the system to be completely output controllable? It's that the rank of this QCO should be P. So there in QC we have the number of states which are n, assumed to be n, and the rank of QC should be equal to the number of states which is equal to n. Here in QCO we are dealing with outputs, and outputs we have assumed that the number of outputs is P. So also the rank of QCO should be P. Okay, so what we are controlling, the number of variables to be controlled, this is the summary. Okay, that whatever we are controlling, whether the output or the states, the rank of the corresponding matrix should be equal to the dimension of the variable to be controlled. So in case of states, we are speaking about n states, and the rank of QC should be n. And in case of output controllability, we are speaking about the outputs, and their number is p. It's a vector of dimension p, and then the QCO should have a rank of p. And let us take the examples regarding this point. Here we have this system. This is the state differential equation, this is the output equation, and in this case D is equal to 0. So we are interested in determining both the state controllability and the output controllability. For state controllability, we have reached to this QC matrix, and when we check its determinant, it was non-zero, and so QC is equal, the rank of QC is 2 and its full rank, and based on that the system is completely state controllable. So we are speaking about the states, they are completely state controllable. And regarding the output controllability, we form this QCO, this is QCO, okay, and finally we will get this matrix, and the rank of this matrix is equal to 1, and the system is output controllable. Okay, so let us take another more complicated example. Here we have state differential equation, and this is the output equation. Okay, and we also want to determine the output controllability and the state controllability. Regarding the state controllability, we determine QC, and we find its determinant based on any of the previous methods that we have covered in chapter 1. So in this, if we take any random columns, non-zero columns, the determinant is -7, which is full rank, or this is the other alternative that we multiplied QC by QC transpose, and finally we will get this M matrix, and we find the determinant of this matrix, which is non-zero, and based on that, since it's non-zero, it's full rank and the states are completely controllable. And regarding the output controllability, we form this QCO based on the previous approach. And if we proceed in the solution process, finally we will get this QCO, and if we determine its determinant, then it will be, if we take any two non-zero columns of this matrix, it will be the determinant non-zero, and this means that this QCO has a rank of 2, and the system is the output, all of the outputs are completely controllable. One more example also, in order to understand everything in this regard for both the output and the state controllability. So again, this is a third order system in terms of A, and seesaw system in terms of U and Y. So we want to evaluate the state controllability and the output controllability. And regarding the state controllability, this is QC, and finally we reach to this QC, and we find its determinant, which is non-zero, and its full rank, and based on that the system is completely, or the states, they are completely state controllable. And regarding the output controllability, we form this matrix, and finally we will reach to this one, and if we select any of the non-zero, it will be the rank which is equal to 1, and the system is completely output controllable. So this is everything regarding the state and output controllability. And now we will switch to the second half of this chapter, which is related to the concept of observability. So the second half of this chapter is related to the concept of observability, and let us explore what do we mean by a system to be completely observable regarding the states. So a system is said to be completely state observable if we can estimate every state, if every state of x of t, okay, can be estimated or identified by the measurement of the output vector, by the measurement of the output vector, okay, over a finite interval of time, assuming that the input vector is also available, then we call this system is completely state observable. Again, state observability is related to the states. And what we mean by observability, that if we have the output vector y of t, if it is provided to us, and through the availability of y and through y, we will estimate all of the state variables based on the availability of y. So over a finite interval of time, if this condition is satisfied, we can say that the system is completely state observable. So if we are able to find all of the states, from x1 till xn from the measurement of the output vector y of t, okay, if we can estimate all of the states or find or identify all of the states x of t based on the availability and measurement of y of t over a finite interval of time, assuming that the control vector or signal u of t is available, then we say that this system is completely state observable. If we cannot determine any of the states cannot be estimated, okay, or identified from the output vector, then we say that this system is not completely state observable. So if all of the states from x1 till xn can be estimated or identified from the measurement of the output vector y of t that is available over a finite interval of time, and the input also is available, okay, then we say that the states of the system, they are completely observable, or the system is completely state observable. But if some of the states are not identified or cannot be estimated from the output vector, okay, then we say that the system is not completely observable, or the states, regarding the states, we say that the states, they are not the system is not completely state observable. Okay, so let us discuss some of the few points in this regard. Observability is related to the problem of determining the system states by the measurements of the output, and this output is available for finite interval of time. So the second note, the concept of observability is dual to that of controllability, duality. So what's controllability? Controllability study the possibility of how to control the state from the input, while observability study the possibility of estimating the states from the output. So in this regard, we have the states, they are common in both the observability and the controllability. If we are assume that the states, they are given, so we have here x of t, and here we have u of t, and here we have y of t. Okay, so u of t, x of t, y of t. So if we can control the states from any initial value x of t naught to any final value x of t f, okay, over this interval between t naught and tf, using any unconstrained value of u of t for all of the states from x1 till xn, okay, then the system is completely state controllable. So state controllability is the relation between the input and the states. This is controllability. While observability is the relation between x and y. Observability gives the description between x of t, the state vector, and the output vector y of t. So this is observability. So if we are able to estimate all of the states from x1 till xn based on the measurement or the availability of the y of t vector, and this availability from y of t naught till y of tf, so over this finite interval from t naught till tf. So if we are able to estimate this x of t, if we are able to estimate this x of t from the availability of y of t over this interval, then the system is completely state observable. And if we are unable to estimate all of the states from the availability of the y, then the system is not completely state observable. So we should understand that controllability is relationship between u of t. Controllability is the relationship, study the effect of u of t over x of t. This is controllability. While observability study the effect of or the possibility of determining x of t from the availability of y of t. While controllability study the possibility of controlling the states from any initial value to any final value through the input vector, and this is what we mean by controllability and observability. And again, this is what we discuss in this point. So the next comment, the controllability and observability, they are defined under the assumption that the state equations, okay, or the state space representation or the matrices A, B, C, D, they are known. So controllability and observability assume that the matrices A, B, C, D or the state space representation of the system is known, and its observability is different from another problem, that is the identification of A, B, C, D matrices. And this identification, it's under a main topic in the general umbrella of control systems, that from the relationship between input and output we can estimate A, B, C, D, but this is not related to the observability. So observability, we assume the matrices A, B, C, D, they are given, they are known to us. The problem of determining the matrices A, B, C, D from the input and output vector, this is known as system identification, which is another main topic in the general umbrella of control systems. So this is the next point. And the next point is when the system is not completely state observable, this means that some of the states are not measurable or they are shielded from observation. Some of the states, if the system is not completely state observable, then at least one of the states cannot be measured from the output vector, or it's shielded from observation. And what about the state observability testing methods? Okay, so we have, as given in the controllability, we have two main methods for checking the observability. Number one is the Kalman test for observability, and number two is the Gilbert test of observability. So they are similar to the tests which were covered in the controllability, with a difference in the application and in the calculation of the matrices. So this method is applied to any form of the pair of matrices A and C. This is in your handouts, in the handouts that's given to you, it's written matrix A. So you should correct this. Instead of the matrix A, correct it to the matrix pair A and C. Okay, and here also it's the same matrix pair. Correct it in your handouts, in the handouts that's provided to you at the start of this semester. It was written A. I have corrected them recently, and here we are speaking about that this method is can be applied to any form of the matrix pair A and C, whether the matrix pair A and C they are in the canonical form or no. So any general form of matrix A and C, it's not, there is no restriction of the form of the matrices A and C. While Gilbert test, it's based on transforming the matrix pair A and C into DCF in case of distinct eigenvalues, or JCF in terms of repeated eigenvalues, and after that we can apply this test for observability. So Kalman test applied directly on the original state space representation by checking the matrices pair, the matrix pair A and C. Okay, and Gilbert test for observability, it requires some transformation from the already given form of the matrices pair A and C to the DCF in case of distinct eigenvalues, or JCF in case of repeated eigenvalues. And after this transformation, we can decide whether the system is completely state observable or no. Okay, so there is one advantage of applying the Gilbert test, as we previously discussed in the case of controllability. So in Gilbert test, we can determine which of the states, in case of we find that the system is not completely state observable, we can find or we can determine which of the states they are not observable. So this is the case of Gilbert test. So the drawback of the Gilbert test for observability is that it requires transformation to DCF or JCF, while the main advantage of the Gilbert test for observability is that after this computational burden of transformation, we are able to determine which of the states are observable and which of the states they are unobservable. So this is the main advantage of Gilbert test. While in case of Kalman test, it's a black box. We cannot determine which of the states they are observable and which of the states they are not observable. It gives you an answer of yes or no, true or false. Whether the system, Kalman test, it gives you whether the system is completely state observable, yes or no. But it does not give you any deep information or any further details about which of the states they are observable and which of the states they are unobservable. While in Gilbert, okay, we pay additional computational burden by transformation to JCF or DCF, but the advantage of Gilbert is that it can give you exact details about which of the states they are observable and which of the states they are unobservable. So we will start with the Kalman test for observability, and in this procedure we find the observability matrix QO, which is of this size, and this is its formulation. In your handouts there is another formulation which is written C transpose then and continue in this, the formulation, the other formulation than this, delete it. It's not okay. So in this equation in your handouts there is another formulation, delete or cancel, it's not okay. So this is the only formulation for the observability matrix. CA, it's a column, okay. C to the power C multiplied by A to the power n minus 1. The other form that's in your handouts, delete it. It's not okay. So after determination of this QC matrix, we find its rank, and the necessary and sufficient condition for the system to be completely state observable is that the rank of QO should be n. The rank of QO should be n. And as I mentioned previously, here we are interested in determining the state vector, and the state vector is of size n. So this QO should be of the rank of the states, should have the dimension of the states which we are speaking about, which are the number of states is n. So if the according to Kalman test for observability, if the observability matrix has a rank of n or full rank, then the system is completely state observable. While if it has a rank less than n, then it's not completely state observable. And here Kalman test for observability, as I mentioned, can be applied to any general form of the matrix pair AC, whether they are in the canonical form or no. And the observability matrix is a square matrix if case of single output, while it will be a rectangular matrix of this size if it has multi outputs. And if the system is not completely observable, completely state observable, then this test, as I mentioned, does not give you information which of the states they are unmeasurable and which are the same, they are shielded from observation. So this test, it's a black box. It tells you that the system is completely state observable or no, but it does not give you information about which of the states they are shielded from observation or they are not observable. Okay. The second test that is used for determining the observability is the Gilbert test. It's the Gilbert test, and we have two forms of Gilbert test for observability. This Gilbert test of observability based on DCF form, and the other form is Gilbert test of observability based on JCF. And DCF or JCF, it will depend on the eigenvalues, whether they are repeated or non-repeated. So as I mentioned previously, from step 1 till step 4, it's the same as the transformation process. It's the same as what we have covered in the similarity transformation. I will not go through this. This is covered in the similarity transformation. And in the fourth step, we are interested in determining two matrices, A and C. In your handouts, there is written B and D. B, T, and DT. They are not written. Delete them. B and D, they are out of the question for us. We are not interested in determination. So we are interested in determining AT and CT. AT, it's for verification purposes. It should be diagonal matrix in terms of DCF. While the most important matrix that determine the observability is the CT, the transformed C, which is equal to C multiplied by the transformation matrix T. Okay, and what's the necessary and sufficient condition for completely state observability? It's written here, the system with distinct eigenvalues. This means that we are applying DCF is completely state observable if and only if no columns of CT has all 0 elements. No columns of CT has all 0 elements. Okay, so the system after evaluation, this CT, after the evaluation of CT, we inspect the CT matrix. If it is a CISO system, then CT or single output system, then CT will be a row vector, only single row. While if the system has multi-outputs, while if the system has multi-outputs, then CT will be a matrix. CT will be a matrix. So the necessary and sufficient condition for the states to be completely state observable is that none of the columns of CT should be all 0 elements. And this reminds us with similar thing which was discussed previously in our previous lecture regarding the controllability. In controllability, we were speaking about BT, the matrix B, transformed matrix, not CT, while in the observability, we are speaking about CT. And in the Gilbert test for controllability based on DCF, okay, we were speaking about that there is no row. Here we are speaking about column. there it was no row of BT has all 0 elements, while in case of observability we are speaking about no column of C of T has all 0 elements. Okay, so to apply this condition, okay, AT should be diagonal form and the eigenvalues should be distinct eigenvalues, and if they are distinct then we can apply the DCF. Okay, if any of the columns of CT has all 0 elements, then the corresponding state is unobservable. Okay, then the corresponding state is unobservable. And let me clarify this point. Let me clarify this point. Assume that CT for CISO system was like this: 1, 1, 1, or any value, and this 0, 2, 5. Assume that CT was like this. Okay, so the concept behind the Gilbert test for observability in case of DCF, it states that no columns of CT should have all 0 elements. And since we are speaking about CISO or single output system, then this 0 is satisfy the condition that is states that the system is not completely state observable, since this is 0 element in case of single output, and since there is a 0, then the system is not completely state observable. So we know that the system is not completely state observable. Here, if you pay attention, this is the first state, second state, third state, fourth state, and this is the fifth state, because we know that y is equal to c multiplied by x. Okay, so this 0 will be multiplied by x4. This means that the fourth state variable is unobservable. So this is the main advantage of applying the Gilbert test. Gilbert test, it specify which of the states they are unobservable. So in our case, in this random example of this is 0 for case of single output system. Okay, correspond to the fourth state, and as a result the fourth state is shielded from observation, cannot be measured, cannot be estimated from the y availability, and while the remaining states from x1 till x3 and x5, they are non-zero, and based on that the system is partially state observable. x1, 2, 3, and x5, they are observable, while x4, it's shielded from observation, it's not observable. So this is the case of CISO or single output system. Now let us cover the case of MIMO or multi-output system. So assume that we have 2 outputs. Okay, then in this case C will be consisting of 2 rows. Assume it was that 1, 2, 3, 4, 5, 6. This is the C. In this case, none of the columns of this matrix is all zeros, and this is completely state observable. While if we take another example of C, okay, assume that it was like 1, 4 in the above case, 0, 0, and here 3, 6. Okay, this means that this is non all 0 element, this is non all 0 elements, while the second one is all 0 elements. So this means that this is corresponding to x1, this is corresponding to x2, this is corresponding to x3. Okay, and based on that, this means that x2 is shielded from observation, x2 is not observable, while x1 and x3, they are observable. So this means that the system is not completely state observable. And which of the states they are not observable? It's the second state, which is equal to x2, while x1 and x3 they are observable. And I wish by this clarification everything is clear for you. So let us continue in the lecture. If the eigenvalues of matrix A are not distinct, then diagonalization is impossible. And this is, we have previously that we know that DCF can be applied only to distinct eigenvalues. We cannot convert it to D matrix, and we should go to JCF, which result in Jordan matrix, not diagonal matrix. Okay. In DCF form, all states are decoupled from each other. Okay. This is from the A matrix. This is known from the A matrix. It's diagonal matrix. Okay. Now we will switch to the last, and this is very important according to what I have discussed on the empty page previously, just a few minutes. If we consider here that the ith column of CT has all 0 elements. Okay. Okay. This means that the ith state variable, okay, will be missing from all output equations. We assume multi-output system with P outputs. Multi-output system with P outputs as given in this equation. As given in this equation. If we check this system, it has how many outputs? Y1, Y2 till Yp. So we have P outputs, how many states? From x1 till xn, n states. So each equation from the output equations, it contains its C elements, C11, C12 till C1n, and finally CP1 till CPn. So here the C matrix is a matrix, not a row. Okay. And here we assume the ith state, this is the ith state, all of the coefficients of this ith state is 0. So if we pay attention to y1, y2 till yp, this, all of them, this xi will be missing in all of the output vectors. This xi will be missing in all. If we write it, 0 means that it's missing. So if we write all of the equations from y1 to yp, this means that the ith variable will be missing. It's not there. And if the ith variable xi is not there, how can we estimate it? How can we estimate xi? Because it's not available. So this means that this xi is unobservable. This means that this xi is unobservable, while the remaining, okay, x1, x2 till xn, they are observable, since we assume that those coefficients in x1, those coefficients in x2, those coefficients in xn, they are non all zeros. They are non all zeros. Okay. And this is what we mean by state observability based on, this is what we mean by state observability based on Gilbert test for the case of DCF form. Now we will switch to the another case of a Gilbert test based on JCF form. Based on JCF form, and as you know, JCF form is applied for the case of repeated eigenvalues. Okay, so the steps from first step till here, they are the same as covered in the similarity transformation. They are as covered in the similarity transformation, and I will not cover. We will switch to the fourth step by finding the matrices, and in these transformed system we only find AT, which should be of Jordan canonical form, and we find only C, as I previously covered in DCF. The matrices B and D, they are not required, and as I mentioned, this J matrix or AT matrix is calculated only for verification that we will have a Jordan matrix, while the most important matrix for the determination of the observability is the C matrix, is the CT matrix. So what's the condition for the completely state observability? So we say the system is completely state observable if and only if: number one, no two or more Jordan blocks they are associated with the same eigenvalues, and this I have previously discussed in controllability and in chapter 1. Okay, so any set of repeated eigenvalues, they will be cascaded in one group of Jordan block, not more than one Jordan block. And the second condition, which is, I will cover the third, the elements of each column of the CT matrix, which is equal to CT, that correspond to distinct eigenvalues, they are not all zeros, and this is similar to the conditions that we previously covered in the DCF form. This is, we covered in the DCF that none of the columns should be all zeros. So what's new? The new is this second condition: the elements of the column, okay, that correspond of CT matrix, that correspond to the first column of each Jordan block, they are not all zeros. They are not all zeros. Okay, so those three conditions, if they are satisfied, then the system is completely state observable. If the second or the third condition, this second condition or third condition, any one of them regarding the distinct eigenvalues here, and in the second condition regarding the repeated eigenvalues. Second condition, repeated eigenvalues, and here for distinct eigenvalues, the third, it should be satisfied. For distinct, it should be the same as in case of DCF. None of the columns that correspond to the distinct are all zeros, while in case of repeated, we are interested only in the first column of each Jordan block. The remaining columns, they are don't care condition, not necessary. So the first column of each Jordan block, they should be not all zeros. And this is what are the conditions for completely state observability for systems with repeated eigenvalues. And if you remember, we discussed that Jordan block in AT matrix, it will have this form, and this condition of state observability, this AT matrix should have in the Jordan form, and this means that the eigenvalues at least should be a pair of repeated eigenvalues. And if none of the columns of CT matrix according to condition 2 and 3, okay, are not all zeros, then are all zeros, sorry, not all zeros, are all zeros here. If any of the columns according to condition 2 or 3 are all zeros, then the corresponding state is unobserved. The corresponding state is unobserved. And let us take examples in order to understand what I have discussed. In this example, we have single input, single output system of two states, okay, and we find this observability matrix. This is the final results. We determine its rank, its full rank. So the system is completely state observable, and this is based on Kalman test. Okay, here we find observability based on Kalman test. Okay, the other example, it's also single input, single output with 3 dimension. The number of states is 3, and also we are interested in determining the observability of this system. Okay, and we find this QO matrix, and finally we will get this matrix, and we find its determinant, and it's 0. And now we go to the submatrix of 2 by 2, and as a result the rank is 2, which is not equal to 3, and as a result the system is not completely state observable. And in the next example, this is a much more complicated example with 4 states. This is much more complicated example with 4 states and single input, but it has two outputs. And we want to check the observability of this system, and this is the QO, and finally we will reach to this system. Okay, we find the value of QO as given, as I have marked, and now we will check the determinant of any submatrix, and it will be 4. It will be non-zero and the rank is full, which is equal to 4, or we find it based on this method. And also if we find it, it will be 4 also, and based on that the system is completely state observable based on Kalman test, for observability. And we continue in the examples. Also this is single input single output of dimension 4, and we want to check the observability based on Kalman test. We will find the QO according to this equation, and finally we end up with this system, and it has a full determinant which is not equal to 0, and as a result the full rank, which means that the system is completely state observable. Now we will switch in the next set of examples. All of the previous examples, they were discussing the Kalman test of observability. Now we will switch to Gilbert test of observability, and here 3 states, single input single output system. Okay, so for Gilbert test, the first thing is that we should find the eigenvalues, and since they are distinct, then we will apply the transformation to DCF. We find this T matrix, and finally we find CT, as I previously discussed, that we are only interested in CT. AT is for verification only, and this is the CT matrix. If we pay attention to this matrix, the first element of this CT is non-zero, and the third element is non-zero, while the second element of this matrix or of this vector is 0. This means that the system is not completely state observable. And which of the states is not observable? This means that this second one is not observable. This means that x2 is not observable, or it's shielded from observation. We cannot throw the checking and the availability of y of t, we cannot determine x2, while x1 and x3 we can, from the availability of the output vector, we can estimate or find x1 and x2, but x1 and x3, while x2 is shielded from observation, we cannot determine. And this is the advantage of the Gilbert test, that it specifies which of the states they are shielded from observation. If we continue in the Gilbert test examples, okay, this is single input single output with 3 states, and we want to check the observability based on Gilbert test. And if we pay attention to the eigenvalues, okay, they are distinct eigenvalues, and based on that we proceed in the determination of the T matrix. I will not go through the details. So finally we will reach to this T matrix, and this is T inverse, although T inverse is not required. So we find the transform matrix CT, which is equal C of the system multiplied by the T matrix, and this is the resultant of CT. And if we pay attention to this CT, all of the elements of CT, they are non-zeros. And what does this mean? This means that the system is completely state observable. The system is completely state observable. And if we also proceed in the examples regarding the Gilbert test, Okay, single input system, single output, 3 states. We want to find the observability based on Gilbert test, and in order to apply Gilbert test, the first thing is that we should find the eigenvalues, and since the eigenvalues they are distinct, so DCF will be transformation will be used, and finally we will reach to this T matrix. I will not go through those details of determining the eigenvectors here. Okay, so finally we will reach this T, and we determine this CT, which is equal C multiplied by T, and this is 1 1 1. And since there is no element of 0 for this single output system, then the system is completely state observable. Again, we will take another example of single input, single output, 3 states, and we will also check its observability based on Gilbert test. And here we find the eigenvalues, they are distinct, and since they are distinct, then we apply the DCF transformation, and finally we will reach to this T matrix, and after that we will find the CT, and CT is determined by multiplied by T. And if we pay attention here, okay, we will get this row vector, and within this row vector the first element is non-zero, the third element is non-zero, while the second element is 0. This means that the system is not completely state observable, and which of the states they are not observable? It will be clearly x2 will not be observable, while x1 and x3 they are okay. So x1 and x3, since they are non-zeros, it's okay. We can estimate x1 and x3 from the availability or the inspection of y of t, while x2 it's shielded from observation. We cannot estimate x2 from the availability of y of t. Okay, let us continue in the examples. Here also we have single input, single output, 3 states, and we want to check the Gilbert test. And if we want, we will find the eigenvalues. We will find the eigenvalues. The eigenvalues, they are here. I think in your handouts there is some intermediate mistake here regarding the roots of the equation, but I think this is the correct one. Please check the answers. Okay, those answers, the eigenvalues, please check them. I think they are correct, but there is something written before this lambda 1, lambda 2, lambda 3. Okay, and if we pay attention to the lambda 1, lambda 2, lambda 3, we easily check that lambda 2 and lambda 3, they are repeated eigenvalues. Okay, lambda 2 and lambda 3, they are repeated eigenvalues. And if we pay attention to the A matrix, it's given in the CCF form. So based on that, we can find the T matrix based on modified Vandermonde or generalized Vandermonde matrix. And finally we will reach to, we find this T, and CT will be this value. Okay, now we will pay attention. Okay, here we said that lambda 1 is the distinct eigenvalue. So this 0 is corresponding to the distinct eigenvalue. This is distinct eigenvalue. While the second and the third elements, they are corresponding to the repeated eigenvalue. So what we mentioned about the Gilbert test for observability for the repeated eigenvalues, we said for the distinct, none of the columns of CT should be 0, and in this system this first one is 0, and this means that x1 is not observable. Okay, regarding this one, the repeated, the columns of CT that correspond to the repeated, we say that the first column that is corresponding to the repeated Jordan, or the Jordan block, the first element of the Jordan block, the elements of CT that correspond to the first. So the first is equal to -1. The first is equal to -1. And this should be non-zero. So regarding the repeated, which will be x2 and x3, they are okay. They are observable. And this 0 in the last element, it's don't care condition. It's weightless. The 0 in the third element, this 0 in the third element, it's 0. It's of no interest. It's of no value. So what's of interest? It's the first column that correspond to the Jordan block. Okay, and this is the element. If this is 0, the -1 is 0 instead of -1, this means that also the repeated repeated states should be also unobservable. While again, let me explain it on a separate page. CT was 0, -1, 0. And this one was corresponding to the distinct eigenvalue, and those to the repeated eigenvalue. So, according to the rule, necessary and sufficient condition for observability based on JCF, okay, that the columns of CT that correspond to the distinct, they should be not all 0. And this is 0. So this means that x1 is not observable, because this is violation of the rule. And if it is 0 here, this means that x1 is not observable. Okay, so this is regarding the distinct eigenvalues, the distinct the rows of the columns of CT that correspond to the distinct eigenvalues, while this is corresponding to the repeated. In the repeated, we are interested in only the first column. So what we are interested in this, in the -1. Is it 0? No. So this means the repeated set is observable. This 0 in the third element, which is not the first of the Jordan block, is don't care. It's wasteless. It's weightless. So whether it's 0, 1, any value, it does not, we don't care. The thing which will determine whether it's observable or no is this one, the first element, okay, the first column of each Jordan block corresponding to the repeated. If this is, since this is not 0, this means that the repeated, they are observable. So x2 and x3 will be observable, while x1, since it's 0, this means that regarding the distinct, this is not observable. I wish that I have clarified this point in a very nice manner such that you will understand it. Okay, let us continue. Okay, we will continue with Gilbert test for observability. Here we have 4 states, single input, single output, and we will find the eigenvalues. Here the eigenvalues, first and second eigenvalues, they are repeated, while third and fourth, they are distinct. Okay, so we will find this T matrix without going into the details, and finally we will find CT, and this is the CT. So this is 1, 0, 1, 1. Okay, this first 2 columns correspond to the repeated, while the last 2 columns, they correspond to the distinct. Okay, here -1, lambda 1 and lambda 2 is the repeated, and lambda 3, lambda 4 they are the distinct. Okay, so the first 2 columns of CT will be corresponding to the repeated, while the first two columns here repeated, while the last two, they will be corresponding to the distinct. So regarding the distinct, since none of them is 0, then the distincts, they are observable. This means that x3 and x4, they are observable. We don't have any problem in estimating x3 and x4. Okay, regarding the repeated, we pay attention only to the first column. Okay, to the first column of CT that correspond to the repeated. If it is non-zero, this means that the system is observable. If it is non-zero, the system is observable. If it is 0, then the system is not observable. And here it's 1. This means that x1 and x2, they are also observable. So the overall system from x1 till x4, it will be all observable. And this 0 in the second element of the Jordan block, okay, corresponding to the second element, it's weightless. It's don't care condition. We don't pay attention. So what's important is that the first column of each of CT that correspond to each Jordan block. Okay, so here the repeated lambda 1 and lambda 2, we are interested in the first element of this CT matrix and the third, fourth element of this CT matrix. All of them should be non-zero. While if the second element that correspond of CT that correspond to the repeated, it's don't care condition, and based on that, the system is completely state observable. And here the 0 elements that meets the repeated eigenvalues not included in the test because it's weightless. Sorry. So we will again continue. Okay, here we have a system of 3 states, single input, two inputs and 2 outputs. System of 3 states with 2 inputs and 2 outputs. So it's a MIMO system, and we will check its Kalman observability test. Okay, so we will proceed. We will find QO based on this equation, and finally we will get this, and we will take any 3 rows and the rank is 3, or QO transpose QO and its determinant is non-zero, then the system is completely state observable since the rank is full rank. Okay, again we will continue. Okay, in the Kalman test of observability, we have single input, single output, 3 states, and we will check the observability based on Kalman test, and we find the QO, and finally we reach to this QO and its determinant is non-zero. This means the rank is 3, full rank, and the system is completely state observable. And I end up this lecture. Okay, I end this lecture at this very important concept of the relationship between controllability and observability and the transfer functions, and I will cover inshallah in the next lecture. Thank you.